The overwhelming power of melting ice, the reality of climate change. Climate change is no longer a distant threat. It is a present reality reshaping our world. From rising sea levels to extreme weather events, the effects of global warming are intensifying. What were once considered freak occurrences, massive storms, flooding, and heat waves, are now becoming common. The Earth's ice is melting, and with it, the face of our planet is transforming. Sea levels are rising, threatening to submerge coastal cities and displace millions of people. Scientists have long warned about the impact of melting ice caps, but now we are beginning to see just how rapidly this change is occurring and how devastating it may become. A global meltdown. Global warming is more than just a phrase. It describes a dangerous trend. As global temperatures climb, ice sheets in Greenland and Antarctica are melting at alarming rates. In 2005 alone, 77 cubic miles of ice from these regions melted into the sea. For comparison, the entire city of Los Angeles uses only about 1 cubic mile of fresh water in a year. The Intergovernmental Panel on Climate Change, IPCC, projected in 2001 that sea levels could rise by about 3 feet by the end of the century. But recent observations suggest this estimate may be outdated. Experts like Professor Bill McGuire warn that the original models underestimated the speed and severity of ice melt. Indeed, even conservative forecasts predict that within 60 years, a quarter of all US homes within 500 feet of the coast could be destroyed. More recent research raises the stakes even further, suggesting that sea levels could rise by as much as 20 feet by the century's end, affecting over 100 million people worldwide. The past informs the future. To predict what lies ahead, scientists study Earth's climatic past. Sea level rise is not a new phenomenon. Throughout the planet's 4.5 billion year history, sea levels have fluctuated due to natural cycles of freezing and melting of polar ice caps. Earth's climate alternates between ice ages, when temperatures drop and ice expands, and interglacial periods, like the one we are in now, when warming causes ice to retreat and sea levels to rise. These cycles are influenced by changes in Earth's orbit around the Sun. Every 100,000 years, the orbit shifts between circular and elliptical shapes. When Earth is farther from the Sun in its elliptical orbit, it receives less solar energy, triggering colder climates and ice ages. Currently, Earth's orbit is nearly circular, which should result in stable, moderate warming. However, what scientists are witnessing today is beyond natural variation. The rate of warming and ice loss is far more intense than expected. Greenland. Ground zero for ice loss. One of the most dramatic examples of accelerated melting is Greenland. Its massive ice sheet spans 836,000 square miles with an average thickness of nearly 1.5 miles. It holds around 600,000 cubic miles of ice. But now, it's rapidly melting. Since 1990, average winter temperatures in Greenland have risen by 46.4 degrees Fahrenheit. Every 40 hours, the Greenland ice sheet loses 275 billion gallons of water, mainly in the form of icebergs crashing into the Atlantic Ocean. Just 10 years ago, the melting rate was only 1/3 of that. One particularly significant glacier is Jakobshavn in western Greenland. Scientists have tracked its retreat since 1850. In that time, it has moved back 37 miles, but much of that retreat has occurred recently. In the last 5 years alone, it has begun retreating at double the previous rate. Currently, almost all glaciers in Greenland below the Arctic Circle are accelerating in their discharge of ice into the ocean. While glacial melting at the edges is normal, glaciers typically maintain a mass balance, gaining snow and ice at the top while losing it at the edges. That balance kept the ice sheet stable for the last 10,000 years. But now, that balance is broken. Greenland is losing 20% more ice than it gains each year. If this continues, the entire ice sheet will diminish steadily, contributing significantly to sea level rise. In fact, it is already shedding around 50 cubic miles of ice annually. NASA's alarming discoveries. To better understand the rapid changes, NASA installed GPS devices across Greenland's ice sheet to measure shifts in elevation and volume. The data revealed something startling. The glaciers weren't just melting, they were accelerating toward the sea. In 1985, one glacier moved about 4 meters per year. By 2003, it had doubled that speed to nearly 8 meters per year. In recent years, glacier speeds have increased by 50 to 80% during warm summers. This acceleration is due to meltwater acting as a lubricant beneath the ice. Physically, it's simple. When ice melts, the resulting water seeps between the glacier and the bedrock. That water reduces friction, allowing the glacier to slide faster toward the ocean. This process, once rare, is now widespread in Greenland. The bigger picture. The situation in Greenland is a preview of what's happening globally. Antarctica is also losing mass, and together these two ice sheets contain enough water to raise global sea levels by more than 200 feet if fully melted. The danger is not just slow rise, but abrupt tipping points. As ice sheets collapse and oceans warm, feedback loops may accelerate melting further. Warming reduces the reflective power, albedo, of ice, causing more solar heat to be absorbed by darker ocean water, which leads to more melting. Moreover, the added fresh water from melting ice disrupts ocean circulation, such as the Atlantic Meridional Overturning Circulation, AMOCI, which helps regulate the global climate. Disruption here could trigger even more extreme weather patterns, droughts, floods, and destabilization of food and water supplies. Conclusion: a call to action. The melting of Earth's ice caps is not a future problem, it is a present crisis. The consequences of rising sea levels will be devastating: submerged cities, climate refugees, and widespread ecological damage. Yet there is still a window of time to act. Understanding the science, updating our climate models, and aggressively reducing carbon emissions can slow down this global meltdown. But delay will only accelerate the pace of destruction. Nature is speaking loudly through rising seas and melting ice. The question now is, will we listen? The melting ice, climate change, and rising seas. Climate change is no longer a distant threat. It's already reshaping our world. Rising temperatures, freak storms, devastating floods, and record-breaking heat waves are now part of our everyday reality. Melting glaciers and ice sheets are triggering a global sea level rise, threatening coastal cities and placing millions of lives at risk. And as scientists study the forces driving this planetary transformation, the evidence is increasingly clear. The climate crisis is accelerating. The term global warming is now familiar to most, but behind the words lies a harsh reality. The Earth is heating up, and the ice that has long protected our oceans and atmosphere is vanishing. In 2005, 77 cubic miles of ice melted from Greenland and Antarctica alone, a staggering loss. To understand the scale, the city of Los Angeles consumes just 1 cubic mile of fresh water per year. These changes have profound consequences. In 2001, predictions estimated sea levels would rise by 3 feet by 2100, threatening over 100 million people worldwide. Today, some scientists fear the rise could be as high as 20 feet. To understand where we're headed, we must look to the past. Sea levels have always fluctuated in tandem with Earth's climate cycles, alternating between ice ages and warm interglacial periods. These changes are influenced by Earth's orbit around the Sun, which shifts shape over a 100,000-year cycle. In a more elliptical orbit, the Earth receives less sunlight, triggering ice ages. In a rounder orbit, we get warmer periods like the one we're in now. But today, something is different. The ice is melting too fast. One of the most alarming cases is Greenland. This vast island holds 600,000 cubic miles of ice, with some areas nearly 1.5 miles thick. If all of Greenland's ice melted, sea levels would rise by about 23 feet globally. Since 1990, average winter temperatures in Greenland have risen by more than 46 degrees Fahrenheit, 8 degrees Celsius, and the rate of ice loss has accelerated dramatically. Glaciers that once moved slowly are now retreating at twice the speed of just a decade ago. Every 40 hours, Greenland loses about 275 billion gallons of water, enough to supply New York City with fresh water for an entire year. The process behind this rapid loss is straightforward. Warmer temperatures melt the glacier surfaces, forming large pools of water. These pools drain through cracks into the base of the glacier, where the water lubricates the ground, reducing friction and causing the ice to slide more quickly into the ocean. This feedback loop is devastating. The more the ice melts, the faster it moves, and the more ice is lost. The natural mass balance that once maintained Greenland's glaciers has been disrupted. Typically, snow falling at high altitudes compensates for the ice melting at the edges, keeping the overall glacier size stable. But now, Greenland is losing 20% more mass each year than it gains. This imbalance is not sustainable, and if it continues, the entire ice sheet may eventually disappear. To monitor this, NASA has installed GPS systems across the ice sheet to measure glacier elevation and movement. The results are sobering. Glaciers are not just melting. They are accelerating, in some cases by 50 to 80% during warm periods. Greenland is alarming enough, but the real giant is Antarctica. Antarctica holds 11 times more ice than Greenland, nearly 90% of the planet's ice and 70% of its freshwater. Until recently, scientists believed the Antarctic ice sheet was stable due to its massive size and frigid temperatures. The assumption was that snowfall at the top of glaciers would balance out any melting at their edges. That belief was shattered in 2002, when a 1,250 square mile chunk of the Larsen B ice shelf collapsed in just 3 weeks. This ice shelf had been stable for over 10,000 years. Its sudden disappearance proved that Antarctica too was vulnerable. The cause, again, was meltwater. Unlike Greenland, where meltwater drains through the glacier, Antarctica's ice cracks don't reach the rock below. So when meltwater seeps into crevices and freezes, it expands by 9%, forcing the cracks apart and ultimately shattering the glacier, a process known as hydrofracturing. This shattering triggers a cascade. Once the ice shelf is gone, the glaciers behind it, previously held back like a dam, flow rapidly into the sea. After Larsen B collapsed, the glaciers it had supported began moving 8 times faster than before. The threat doesn't just come from above. Antarctica's glaciers are also melting from below, as ocean temperatures around the continent have risen by more than 1 degree Celsius over the last 50 years. This warm water circulates under the floating ice shelves, melting them from the bottom at rates up to 162 feet per year. Water conducts heat 25 times more efficiently than air, making this an especially dangerous process. This double assault, surface cracking and basal melting, is destabilizing West Antarctica. Currently, the continent is dumping about 26 cubic miles of ice into the ocean every year. If all of Antarctica's ice were to melt, sea levels would rise by more than 150 feet. New satellite technologies have given scientists a clearer view of these changes. NASA's glaciologist Eric Rignot monitors Antarctic glaciers with pinpoint accuracy. Until recently, many of these glaciers were barely mapped, let alone understood. Now, thanks to satellite imaging, we know they are accelerating and collapsing. To understand how this crisis fits into Earth's long climate history, scientists drill deep into the ice. Glaciologist Richard Alley and others have retrieved ice cores from Greenland and Antarctica that serve as time capsules, capturing ancient air, dust, and atmospheric gases. These layers record past climate cycles, volcanic eruptions, and the presence of greenhouse gases. The results are striking. Ice cores show that carbon dioxide, CO2 levels, and temperatures have always moved together. When CO2 is high, so is temperature. Today, both are rising faster than at any point in the past 800,000 years. CO2 traps heat in Earth's atmosphere. It acts like a blanket, preventing heat from escaping into space. Many scientists now agree that human activity is the driving force behind this warming. Industrial emissions, deforestation, and the burning of fossil fuels have pumped massive amounts of CO2 and methane into the atmosphere. These greenhouse gases are supercharging the natural warming cycle. We are witnessing a planetary shift, one that's not part of the normal rhythm of Earth's glacial cycles. Sea level rise, driven by melting ice sheets, could force the relocation of hundreds of millions of people. Coastal cities may disappear, ecosystems will collapse, the economic and humanitarian costs will be enormous. This isn't just a forecast, it's already happening. But the science is also a call to action. If we reduce emissions and slow the warming, we may still protect parts of the cryosphere. But the window is closing fast. The melting ice is more than a symbol of climate change. It's a warning, one we can no longer ignore. Carbon dioxide levels are rising in the atmosphere. So what does that mean? Most scientists agree it's going to get warmer. One compelling piece of evidence for this connection lies in the data gathered from Antarctica. Looking at the blue line, which represents Antarctic temperatures, and comparing it to the red line for atmospheric carbon dioxide, we see a pattern going back 440,000 years. Temperatures went through regular cycles of warming and cooling, glacial and interglacial periods, driven by shifts in the Earth's orbit. These include changes in axial tilt, orbital shape, and how much solar radiation each hemisphere receives. However, there's a strange detail. During some cold periods, Antarctica was receiving more sunlight than during warmer periods. That puzzled scientists. The explanation came when they noticed that carbon dioxide levels were also lower during those cold spells. When it was warm, CO2 was high. When it was cold, CO2 was low. This revealed a powerful link. Atmospheric carbon dioxide levels and temperature rise and fall together. That connection is not new, it's ancient. But what's happening now is different. Since the Industrial Revolution around 1850, human activities, especially burning fossil fuels and deforestation, have drastically increased CO2 levels in the atmosphere. It's not just a natural cycle anymore. We know exactly where the added CO2 is coming from, and it's changing the planet's climate in very real and measurable ways. As we look into the future, models predict varying outcomes depending on economic growth, global cooperation, and efforts to curb emissions. But in every scenario, CO2 continues to rise. Even beyond the year 2100, the effects will not stop. If we do nothing to curb emissions, CO2 concentrations could rise by 30% over the next 50 years, causing global average temperatures to increase by as much as 10 degrees Fahrenheit. That would make the Earth hotter than it has been in the last million years. And as our world becomes more crowded and polluted, understanding these changes becomes even more urgent. Until recently, we didn't know how soon Earth might face a climate tipping point. Now, evidence from ancient life forms suggests it may happen much sooner than expected. Most people see the ocean as a source of peace or recreation, but rising seas could soon threaten our way of life. It's estimated that within 30 years, 75% of the world's population will live in coastal zones. If major ice sheets melt, cities from Shanghai to New York could be underwater by the end of the century. Not all melting ice raises sea levels. It depends where the ice is. When sea ice, which is already floating, melts, it doesn't raise the water level. It's like an ice cube melting in a glass of water. But land-based ice, like the glaciers of Greenland and Antarctica, does add water to the oceans when it melts or carves into the sea. If Greenland's ice melts entirely, sea levels could rise by 23 feet. In 2001, a 3-foot rise was considered likely, but new discoveries suggest it could be much worse. Evidence comes from coral reefs, living organisms that grow only in shallow, sunlit waters. Fossilized coral reefs from 130,000 years ago, discovered by Dr. Jonathan Opek and his team at the University of Arizona, are now found far above today's sea level. These ancient reefs reveal that sea levels were between 13 and 20 feet higher than today. By analyzing ancient ice core data, scientists calculated that Arctic summer temperatures during that period were only 5 to 8 degrees Fahrenheit warmer than today. Originally, scientists thought we wouldn't reach those levels until the end of this century. But recent trends show that the Arctic is warming faster than expected, meaning we could cross that threshold by the middle of this century. The mechanisms that caused massive melting in the past are the same ones unfolding now. Back then, warm ocean waters melted the underside of ice shelves, causing them to collapse. Without the buttressing ice shelves, glaciers behind them surged into the ocean, accelerating sea level rise. This is exactly what happened in 2002 with the collapse of the Larsen B ice shelf in western Antarctica, as discovered by glaciologist Eric Rigneau. What surprised scientists was how quickly the shelf disintegrated, just 3 weeks, and the fact that land-based glaciers behind it then accelerated their movement to the sea. This kind of melting is now occurring both at the surface and underneath the ice sheets. Surface meltwater penetrates cracks in the ice. When it refreezes, it expands, forcing the cracks wider, eventually breaking the glacier apart. At the same time, warmer ocean water, now over 1 degree Fahrenheit warmer around Antarctica, melts the base of the ice sheets at rates of up to 162 feet per year. The two processes, surface cracking and basal melting, are destabilizing major parts of the West Antarctic ice sheet. Currently, Antarctica is losing 26 cubic miles of ice into the ocean every year. If the entire Antarctic ice sheet melted, it would raise global sea levels by 150 to 200 feet. It contains 90% of Earth's ice and 70% of its fresh water. Just a few years ago, scientists believed it was stable, but satellite data have proven otherwise. This is no longer theoretical, it's observable. Earth may be approaching a climate tipping point, a critical threshold beyond which changes become self-reinforcing and unstoppable. Just a few degrees of additional warming could push our planet past this threshold, causing feedback loops that accelerate climate change even further. To illustrate the potential impact, Overpeck's team ran computer simulations focusing on the New York metropolitan area. A 3-foot sea level rise would flood Fire Island and parts of coastal Connecticut and New Jersey. At 6 feet, the flooding becomes more extensive. At 10 feet, large areas of New York City would be submerged. By 13 or 14 feet, much of the city would be underwater, including heavily populated areas. And New York is relatively lucky. It has some higher ground. Florida, on the other hand, is extremely vulnerable. Most of its population centers are right along the coast, with very little elevation to protect them. All of this paints a clear and urgent picture. Sea level rise isn't a distant threat. It's already happening, and the worst is yet to come unless we take immediate, global action to reduce greenhouse gas emissions. The choices we make in the next few decades will determine the planet we leave for future generations. Climate change, melting ice, and the future of our planet. The planet is warming, and we know why. The rising levels of carbon dioxide, CO2, in the atmosphere, largely driven by human activity since the Industrial Revolution, are the central cause. By burning fossil fuels and cutting down forests, we've significantly increased atmospheric CO2 concentrations. This triggers a well-understood climate response. As CO2 rises, so does global temperature. Evidence from Antarctic ice cores going back 440,000 years shows a clear link between CO2 levels and temperature. When CO2 was low, Antarctica was cold. When CO2 was high, it was warm. This correlation, repeated over multiple glacial cycles, is a strong indicator of the climate's sensitivity to greenhouse gases. The current CO2 rise is not natural. It began accelerating in the 1850s with industrialization and continues unabated today. Climate models predict that if emissions remain unchecked, CO2 could increase by 30% in the next 50 years. This could raise global temperatures by nearly 10 degrees Fahrenheit, creating a climate hotter than any time in the past million years. But rising temperatures aren't the only concern. One of the greatest threats we face is from melting ice and the resulting rise in sea levels. Icebergs, mountain glaciers, and the massive ice sheets covering Greenland and Antarctica are all melting. While floating ice doesn't raise sea level when it melts, ice on land does. If Greenland's ice melts or breaks off into the ocean, it adds volume, pushing sea levels higher. Scientists originally estimated sea level could rise by about 3 feet by 2100, but newer evidence suggests the situation could be far worse. Coral reefs, formed only in shallow, sunlit waters, have been discovered 20 feet above current sea level, dating back 130,000 years. That implies that sea levels were dramatically higher then, during a period only slightly warmer than today. Jonathan Overpeck and his team used fossil coral data and ice core records to reconstruct past climate conditions. Their findings revealed that Arctic summer temperatures were only 5 to 8 degrees Fahrenheit warmer than today, yet sea levels were up to 20 feet higher. This suggests that if current warming trends continue, we may reach those temperatures not by the end of the century, but by mid-century. That would dramatically increase the risk of massive ice sheet collapse, particularly in Greenland and West Antarctica. The processes driving this ancient sea level rise are alarmingly similar to those occurring today. Ocean water is warming and melting the undersides of floating ice shelves. As these break apart, they allow the grounded ice behind them to slide into the sea more rapidly. This ice shelf buttressing effect is critical. Remove the shelves, and ice flow accelerates, raising sea levels much faster. These insights point to a potential tipping point where warming causes irreversible ice loss and unstoppable sea level rise. Overpeck's simulations of areas like New York City show flooding scenarios from 3 to over 14 feet. At higher levels, large swaths of heavily populated urban areas become submerged. Florida faces even greater risks due to its low elevation, with much of the coastline potentially underwater by 2100 if trends continue. Currently, about 2/3 of the world's population lives within 60 miles of the ocean. That puts billions at risk of displacement and infrastructure damage. Even though sea level and temperature are rising gradually now, Earth's climate system contains feedback loops that may accelerate the process. One major feedback is the loss of polar ice, which reflects sunlight away from Earth. As ice melts, it exposes darker ocean water, which absorbs more sunlight. This causes more warming, more melting, and so on, a self-reinforcing cycle. This property is known as albedo. White ice reflects up to 80% of solar energy, while dark water reflects only about 20%. To illustrate the effect, geophysicist Dr. Don Perovich conducted a simple experiment, placing a whiteboard and a blackboard under sunlight. Initially, both were the same temperature, but after a short exposure, the blackboard heated to 120 degrees Fahrenheit, while the whiteboard remained much cooler. This demonstrates why losing Arctic sea ice contributes directly to global heating. In 1979, Arctic sea ice covered an area roughly the size of the continental US. By 2005, the ice area had shrunk dramatically, equivalent to losing everything east of the Mississippi, and this decline is accelerating. If trends continue, the Arctic could be ice-free during summer by 2045, or even sooner. At some point, the system may pass a threshold where recovery becomes impossible, even if emissions are curbed. Meanwhile, warmer oceans not only melt more ice, but also intensify weather patterns. Heat is energy, and warmer seas energize hurricanes. As water evaporates from the ocean, it fuels storms. The hotter the water, the more powerful the storm. Since the mid-1970s, the duration and maximum wind speeds of tropical storms have increased by about 50%. The 2005 hurricane season was the most active and destructive on record. Hurricane Katrina was a turning point for public awareness, but it may be just the beginning. Future hurricanes are expected to be stronger, wetter, and more destructive, especially in coastal cities. Storm surges, a rise in sea level due to low atmospheric pressure and high winds, become even more devastating in a world of higher sea levels. Cities like New York are especially vulnerable. In 1992, a strong nor'easter storm flooded downtown Manhattan and parts of Long Island. Subways were submerged, infrastructure paralyzed. If a similar storm struck in the future with just a few extra feet of sea level rise, the damage could be catastrophic. Northern hurricanes, unlike their southern counterparts, often move faster and deliver stronger winds on one side due to their speed. Experts like geologist Professor Nick Koch warn that even a Category 3 storm could cause Category 5 level damage due to this effect. The implications are sobering. Coastal cities, many of the world's economic centers, are at risk. Ice is vanishing. Oceans are warming, storms are intensifying. These changes are part of a larger systemic shift, one that we may not be able to reverse if we cross critical tipping points. Human activity has already made a measurable impact. The question is no longer whether we've changed the climate, but how much more change we are willing to allow. Without urgent reductions in greenhouse gas emissions, our trajectory could lead to conditions not seen for millions of years, ushering in a planetary meltdown that we may be unable to stop. Facing the flood, New York's vulnerability in a warming world. In recent years, we've begun to glimpse the future effects of climate change, and it is deeply troubling. The 1992 nor'easter that battered the New York City area was a wake-up call. Parts of Manhattan lay under 4 feet of water. LaGuardia Airport was shut down, and wave heights reached 24 feet at the shoreline. And yet this wasn't even a hurricane, it was just a particularly bad storm. Scientists and emergency planners fear something much worse, a strong northerly hurricane striking New York in an era of rising seas. Dr. Nick Koch, a geologist and hurricane expert, warns that New York and the surrounding metropolitan region are among the most dangerous places to be during a major storm. The danger, he explains, comes down to geography. The long curved shape of Long Island and the New Jersey coastline forms a right angle that acts like a funnel during a storm. If a hurricane approaches the city from the south, the counterclockwise rotation of the storm's winds would drive an enormous surge of ocean water directly into this coastal corner. And you can't force water into a right angle without it rising rapidly. Under such conditions, scientists predict that the Statue of Liberty could see storm surge heights of up to 22 feet, with Jamaica Bay potentially facing 28-foot surges. This massive wall of water would crash through the coastline, submerge entire neighborhoods, and surge into the city at terrifying speed. The last major hurricane to hit the region was in 1938. It killed over 600 people and caused what would today amount to $5.4 billion in damages. But in a world where sea levels are higher and storms are more intense, the consequences would be exponentially worse. In such a future event, no borough would be spared. Hundreds of square miles could flood, rendering New York virtually non-functional. Subways would be inundated, tunnels impassable, and hundreds of buildings severely damaged. John F. Kennedy Airport and Battery Park could end up under 10 feet of water. Power and communication systems would collapse, emergency services would be crippled, millions would be displaced. The cost of rebuilding would be staggering, hundreds of billions of dollars, and some areas might never fully recover. The greater New York metropolitan area, home to over 20 million people, could face the kind of evacuation and social disruption we've never before witnessed on this scale. It would be a catastrophe of unimaginable proportions. This isn't science fiction. It's a near-future scenario that scientists believe is likely unless we take significant and immediate action. The ice caps are melting. Sea levels are creeping higher every year. More alarmingly, we may be approaching a climate tipping point, a moment beyond which these processes accelerate irreversibly and human efforts to reverse them become ineffective. But amid the grim projections, there is hope. History has shown us that humanity can recognize a planetary-scale problem and solve it. One compelling example comes from an unexpected source: lead pollution in Greenland's ice. Let's go back to the year 1750, just before the Industrial Revolution began. Human use of lead in products like paint and batteries increased dramatically, and eventually lead was added to gasoline to improve engine performance. As a result, lead pollution spread globally, reaching even the pristine snowfields of Greenland. Then came the Great Depression and World War II, which temporarily reduced industrial activity. But afterward, lead emissions surged again with the booming economy and explosion in automobile use. Eventually, scientists and public health experts sounded the alarm. Lead was toxic, particularly to children. It was damaging our brains, weakening our bodies, and polluting our environment. We were literally making ourselves sick with progress. So societies decided to act. Governments passed laws banning lead in gasoline and household products. Industries adapted. And remarkably, the concentration of lead in Greenland's snow began to drop. The results were visible and measurable. When we stopped polluting, the Earth began to heal. This example shows that we have the power to change course. If we were able to get the lead out, perhaps we can get the carbon out as well. By investing in renewable energy sources such as solar and wind, improving energy efficiency, and rethinking our transportation and agriculture systems, we can drastically cut greenhouse gas emissions. With bold international cooperation, responsible policy, and citizen commitment, we may yet avert disaster. But time is short. If we wait until the effects are unavoidable and catastrophic, when cities like New York are already underwater, it will be too late. The cost of inaction is steep. A world ravaged by climate-induced chaos, suffering from extreme weather events, rising poverty, mass migration, food shortages, and social instability. We face a choice. We can continue on our current path, risking an unrecognizable future filled with human tragedy and economic collapse. Or we can act now and build a cleaner, safer, more sustainable world for ourselves and for future generations. The story of Lead shows us what's possible. We polluted, we recognized the danger, we changed, and it worked. Now the question is, can we do the same with carbon dioxide? The answer will define the future of life on Earth.